let's first look at what does DFT do. Actually, the Fourier analysis told us any periodical signal can be expressed as linear combinations of sines and cosine functions. So let's look at the first function. If I ask you, well, which cosine partial are there in that first function, well, it's very easy for human to judge that it's the time is 1 second and it has 2 periods, so that's 2 hertz, right? But for the second signal, it will be harder for you to decide through the time domain. It's a little bit complicated. Actually, it's a lot very easy. It consists of 2 hertz and 5 hertz partials, but it will be hard for you to judge from the time domain only. And the third one will be a lot harder. It has 3 with different amplitudes and even phase shifting. So basically, DFT does this for us. It will produce a result like, well, this signal has 3 components. The first one with amplitude 1, frequency 2 hertz, and phase of pi over 3. Okay. So then, how does DFT calculate this? Let's look at a simple example. This is a cosine wave. I sampled it 40 times within 2 periods. So the equation will be like this. So now, for now, let's forget about the sample frequency, forget about the time. Only look at the beams. I sampled 40 times within 2 periods. And if I ask you to determine how many times that this cosine wave oscillates in 40 samples, well, you will tell me 2, right? You can count 1 and 2. But the way the computer does this is quite a brute force method. So what is this method look like? First, I'll choose 40 basis signals. The first looks like this. It oscillates 0 periods in 40 samples. So it's basically a constant signal. And the equation is like this. And the second, it has 1 period in 40 samples, and 2 periods, until a signal contains 39 periods in 40 samples. You might wonder how this signal looks like. Well, it actually looks like this. Exactly the same as the second signal. And it's easy to judge from the equation because you know this and this are equal, right? If you add them up, it's 2 pi. Right? Okay. Actually, for the samples, for the basis signals after or more than 20 periods in 40 samples, they actually lose kind of information because there's a concept in signal processing called Nyquist frequency. It tells you that if you want to keep information of the signal, you need to at least sample twice in 1 period. However, if you only, if you sample 40 samples in 39 periods, for 39 periods, you only sample 40 times, it's far not enough. So basically what we concern mostly is the first 20 basis signals. Okay, then what what we'll do next, I compare my original signal with all the 40 bases. And how do I compare? There's a formula let you calculate the correlation between two functions. It looks like this. It's actually the inner product, if you know inner product, right? You calculate this by multiplying each of the function value and add them up. Any question here? Okay. Okay, now we got, let's say how it works. This is the original signal. It's cosine 2 pi to 1 over 40. Looks like this. And this is the, it's actually the 8th basis signal, but it has 7 periods in 40 samples. And we store the result of this in another array given a capital X. And this 7, exactly this 7. So capital X of 7 is the comparing result of the original signal with the signal which has 7 periods in 40 samples. Okay, let's calculate this and see what happened. In this specific example, we found the second and the 38th basis signal give us the highest result. And if you calculate this and this, you get a result of 20. And that means capital X of 2 equals capital X of 38 equals 20. Right? And for other basis signals, that means when k does not equal to 2 and 38, they are all 0. I mean, for this specific example. So we get x0 equals, so all these values are the zeros. And if we plot a capital X array, we get a figure like this. So that is basically, you are a little bit familiar with, but you still don't know what that this means, right? Okay, let's move on. Any problems with this plot? Okay. Okay, let's move this formula. Look at this formula. Move it here. So the k here means I'm comparing with the signal which oscillates k periods in 40 samples. And if I substitute the signal length, 40, with capital N, which means the signal can be any length. And I substitute the original function, this, with x of n, which means it can be any function. Then I get a general notation of this formula, right? Problems? Okay, good. Okay, now I want you to look at the formula of DFT. It's actually looks like this. They're different. And you already know what this formula does. But the the exponential looks scary, so let me expand it in the Euler function. And what we get is, you may notice that this term is exactly the same as this term. However, what is this used for? Why do we want to use a complex number in DFT? Why using complex numbers? Do you have any idea? Anybody? Okay, don't worry. Let's move on. It's okay. Well, actually, if we only compare with the cosine basis, we lose the phase information. Let's look at an example. I shift the original signal by pi/3, right? And let's do it again. And I found x of 2 equals x of 38 equals 10. It was 20 before, but now it's 10. And for other partial, they are all zeros. And if I plot this array, well, actually, except for the change of magnitude, nothing changed. And if you believe me, this signal, I divided by 2 of the half of the original signal, will give exactly the same result here, right? Because I divided by 2, so the magnitude should divide it by 2. So we actually cannot reconstruct the original signal. We don't know whether it's this or this produce this spectrum. So we lose information actually. The solution is quite straightforward. Sorry. We compare with another 40 bases of sine waves. And then we produce 2 arrays, right? One for cosine comparing and one for sine comparing. The length of these arrays are 40, or the signal length capital N. Well, let's calculate again with the sine function. And I found capital X sine of 2 equals capital X sine of 38 equals 10 times square root of 3. And if you still remember that in the cosine comparing, it's 10. Have you discovered something? Yeah. So if we combine the 2 results into one complex number, seems like you can work out the magnitude before using its norm. And actually, the complex number, well, you can look at it as a tool to store the 2 arrays simultaneously. And why don't we use just 2 arrays? Why don't we want to use why do we want to use a complex number? Well, let's look at how to work with the complex number first. This is our result. So the result is 10 plus 10 times square root of 3. Okay. If we calculate the magnitude and phase of this complex number, okay, we get exactly the previous result, 20. And if you remember, pi/3 is exactly the phase what we are expecting. So now we don't lose any information anymore. We can reconstruct the original signal with this complex number. Well, do we have any questions until now?
What is big N again?
Sorry?
A big N. Like 40.
Capital N,
Yeah.
signal length. Well, I actually have one question to ask you. If you remember, capital X of cosine, actually it's the correlation between the original function and the cosine basis, which oscillates twice in 40 or capital N samples, right? So the capital X of sine is also a correlation. So why two correlation? We write two correlations here and we get such a magical result to reproduce that thing. Well, the math behind this is really a little bit beyond this course. It's actually, if you have learned Fourier analysis or real analysis, sine and cosine are orthogonal. You might have heard this. So the correlation function, it is exactly the inner product, right? And when you do the correlation between the original function and the cosine base, you're actually projecting your signal onto that cosine frequency. And of course, you're projecting again to the sine frequency. And since cosine and sine are orthogonal, you can reproduce that signal using this method. Well, if you know this formula, it will be easier for you to understand. If fx equals a times sine nx plus b times cosine nx, then it will be exactly the same as this one. Well, if you don't know, don't worry. Just remember that. Remember how to calculate the magnitude of the phase. The mathematical the mathematical background behind this is really hard and really deep. So don't worry. Well, so until now we haven't talked about the frequencies. We're dealing with beats, right? X1, X2, X3, but we don't know what frequency does X1 stands for, what frequency does X2 stands for. But we do know one thing. X2, I mean capital X of 2, stands for or denotes the correlation between the original signal and the cosine base, which has 2 periods in n samples. So if that correlation is high, that means the original signal has higher frequency partials in the frequency. I don't know what frequency it is, but just that frequency which oscillates 2 periods in 40 samples. Okay, but what frequency is that? The answer is we don't know, unless we're given a sample rate, right? Problem? Okay. If I give you a sample rate, then the basis oscillates k periods in n samples, we can calculate the total length. It's n divided by the sample rate, right? If the sample rate is 100 hertz, that means one sample means 10 milliseconds, and well, if you have capital N samples, then the total length of the sample will be this. And it has k periods, so each period will have a time length of this. So that means the frequency of this exact cosine basis is this. Just calculate in your brain very quickly because it's not hard, right? Okay. So the capital X, each capital X will correspond to a frequency like this, right? Okay, let's do an example. Again, this is our original signal. And if I give you a sample rate of 4,000 hertz, and a capital N, or the signal length, is 40, then one frequency being will equal to, if you remember the formula here, will equal to N divided by Fs, Fs divided by N, hertz. That's 100 hertz. And now I found that the peak appears at capital X of 2 and capital X of 38. So the frequency that capital X of 2 is denoting is 200 hertz. Because one frequency being denotes 100 hertz. So this is X2. So that's 200 hertz. If it's X1, that'll be 100 hertz. If it's X0, that means a constant value. And of course, there's another frequency here that's 3,800 hertz, but we don't care about that because if you remember, I mentioned before we lose the signal information for the second half of the spectrum. So we only care about the first half. So that means if I give you a sample rate of 4,000 hertz, the frequency of this signal will be 200 hertz. Make sense? Okay.
I have a question. Why was it that we lost the information in the second part of the spectrum?
Oh, because we're not, we do not have a, yeah, let's look at the cosine basis. Yeah, this one. We are sampling 39, the cosine basis has 39 periods in 40 samples, but we only sampled 40 times. The Nyquist frequency tells us to sample that frequency, I mean, it oscillates 39 times. At least we need 78 samples to keep the information.
Because otherwise there could be like a period between samples where there would be.
Yeah, you can see that we lose a lot of information here for the last. It should be you can judge from the image that it has 39 periods, right? That's how we lose information. But if you ask about the mathematical background, why the frequency should be, or why we have to sample twice in one period, that's also beyond this course, I think. It's a bit hard to prove. Just you have to sample twice, at least in one period. Okay, where will we? Yeah. Other question? Okay. Okay, let's recall the first example. If I want to derive or calculate these frequency partials using DFT, how do I do it? It has 100 samples in 1 second. Well, the first thing I would do is to change the notation to discrete notation. Let's forget about the time. It's not 1 second, now it's 100 beats only. And we do the DFT. And after DFT, the result will be like this. X of 2 equals x of 98 equals this complex number. And x of 4 will equal to minus 100j, and x of 5 equals 25. How do we reconstruct the signal using these values? First, let's calculate the magnitude and phase. Well, for since x4 and x96 are different, I only calculate the magnitude and phase for x4 because that's the frequency we're caring about. You have problems with the calculation here? No? Cool. And of course, for k does not equal to these values, they are all 0. So the phase information has already been proved by, being provided by the phase here. We can see, right? Sine function is actually to 3 pi over 2 ahead from the cosine function. Right? But how we reconstruct the amplitude here? 1, 2, and 0.5 using these values. Well, to prove it, I need a lot of mathematical derivation, but I want you to remember just for real signals, just divide the magnitude here by n over 2, and we get the signal amplitude. Here, capital N, or the signal length, is 100, and n over 2 is 50. So if we divided this magnitude by 50, we get the amplitude here. And then I give you a sample rate of 100 hertz because this is one 1 second signal. And then the signal length will be 1 second. So capital X of 2 represents the frequency which has 2 periods and 100 samples. That means 2 periods in 1 second, right? That means 2 hertz. And amplitude, yeah, we can derive an amplitude here. Well, similarly, we get the result of x4 and x5, and we transform it into frequency and amplitude. That's how DFT works. So before I move on, I want to make sure you understand all this please ask any questions. So let's recap all the slides again very fastly. Because some people are late, so I'll be very fastly go through it again. And first, we tell you we want to know what does DFT do. Actually, for any periodical signal consists of cosine sine waves, and DFT actually will produce a result like this. And how does it do this? So, if I give you a 40 sample, if I sample a cosine wave within 2 periods, and how does computer calculate the frequency? It choose 40 cosine bases, right? And here we only care about the first 20 bases because we lose information in the second half. And then I compare the original signal to all the 40 bases. How do we compare? We use a correlation function. Looks very similar to the inner product of 2 vector. And if you look carefully, this is the original signal, and this is the signal who has 7 periods and 40 samples, and we store them in x of 7, capital X of 7, and similarly we produce x of 0 to x of 39, right? Then, if we calculate the specific example, we found for this cosine, for our original function, which is a cosine function, if we compare them, if we compare it with the second and the 38th basis signal, we get highest value of 20. For other basis signals, the results are all 0. And if we plot the X array, it will be like this. And then if I substitute the signal length with capital N, and I substitute the original function with x of n, which means the signal can be any signal or any length, it gives us a notation like this. And now I recalled the DFT formula, and I found they are different. And if I expand the DFT formula with Euler equation, and we get this. And the first term is exactly the same as what we calculated just now. But the second term, actually, it's a comparing with the sine basis, right? So, and we lose information, the phase information when comparing with cosine basis. So I gave you an example. It produced a similar result, but try to persuade you that if you believe me, this signal will produce exactly the same spectrum array as the phase shifted signal. So we lose information because we don't know what the original signal will be. The solution would be to compare the original signal with another 40 sine bases to produce another array. And the complex numbers are actually a tool to store the array, the 2 arrays. Okay, if we calculate the magnitude and phase of the exact complex number, we get the magnitude and phase of, it's not the magnitude of the original signal, but the phase will be exactly the original phase. And it's a bit hard to understand the mathematical background here, so just remember to calculate the magnitude and phase here. And for the discrete signals, if I give you a sample rate, then the beams can be transformed into hertz, right? And each value of the capital X array corresponds to the frequencies. So actually, the sample rate divided by capital N is actually the frequency resolution, right? So you can only divide, separate the, or you can only, how to say that? In this example, one frequency beam it's 100 hertz, right? Remember? So if we have a signal contains two very close frequencies, like 100 hertz and 110 hertz, then it will not succeed in separating them. That's what I'm going to continue later. But now, please make sure you understand this. So we're only caring about the first half, so that's F1. And then at last, I gave you an example to calculate the original signal, the different frequency partials of the original signal. That's all. Okay, no problem, right? Okay, so that's how we calculate DFT. And now I want to give you some tricks or techniques when people use mostly in industry when you really want to implement DFT into your projects. What should you do? The first one will be zero padding. As I mentioned, we mentioned frequency resolution, right? Let's look at an example. Here is a random signal with length of n, and actually the DFT, the length of the capital X array we mentioned before is exactly capital N. They are the same length of, it's the same length of the original signal. But if we pad zeros after this original signal and produce a 16 length array, then we conduct a DFT with a length of 16 to produce this. Very clear about what I'm talking about? Okay. And if I increase the number of beams, if I increase the number of zeros I pad after this signal, our spectrum becomes smoother and smoother. In other words, we actually increased the frequency resolution, right? Problems? Okay. I'll give you an example here. This is my signal, and it contains two very close frequencies. And if I do a DFT of length 8192, it's like this. But if I increase the DFT length plot will be very smooth and easy to discriminate, and it will give you a very accurate frequency, right? But in this figure, even if you can choose a maximum here, it's not accurate. So that's zero padding. Okay, so now I want to tell you what is FFT. You might have heard this a lot of times, and you don't know what's the difference between FFT and DFT. Actually, FFT is not one algorithm. It's fast Fourier transform, because DFT takes a lot of time to calculate. Many scientists have proposed their own FFT algorithms. However, today, when we talk about FFT, it mostly refers to an algorithm published by James Cooley and John Turkey in 1965 for the purpose of detecting the Soviet Union nuclear test. That's a true story. They actually improved the calculation of DFT significantly. Like if you do DFT length of 32K and 768, the time consumption will be around, I mean, if you do with original DFT method, it will be around 10 to 20 seconds. But now if you do with this FFT method, it will be only 0.0001 second. So that improves a lot. I'll tell you a little bit about how this FFT algorithm works. Actually, they discovered that for DFT with a length of n, and if n can be decomposed or factorized into n1 times n2, then this long DFT can be separated, divided into two shorter DFTs. And since the time complex of original DFT is O to the n minus n squared, then this actually decreases the time complexity, right? However, if n equals a power of 2, then n1 and n2 can continuously be decomposed into 2, right? So the time complex will be lower and lower. This is the figure in their paper. I actually don't understand that, but that looks cool and tells us they use symmetry to solve this problem. Actually, when capital N or the signal length equals 2 to the power of 2, the algorithm reaches a time complex of O to the n log n. So that's the FFT. Okay, next I will introduce you windowing. Windowing is actually very useful because now we only assume that the signal oscillates integer periods within n samples, but that won't happen in real industry, right? So if we take a non-integer period signal, like the first one is I sample a cosine wave for 256 times within 4 periods, and for the second signal I cut it here. But their frequency should be the same, right? Then I do, if we take 256 points of FFT, I mean, I pack zeros here. the capital X of 4 should be the peak, right? Because it has 4 periods in capital N samples. Well, let's see what happened here. For the first signal, no problem here. And for the second signal, although we successfully pick X4, but yeah, this looks like the main magnitude of capital X4 is lower actually. You can see this is 100 and this is 120. It's lower. Instead, those things increases. So it looks like a frequency leakage. The main frequency leaks to other noisy frequencies. Well, that is actually because in the DFT theory, we are assuming that the signal is infinite, of infinite length. So for a finite signal, we're actually shifting them to produce an infinite signal. We didn't do this in implementation, but actually it's the mathematical background behind this tells us if the signal is infinite length, then it can be represented by sine and cosine wave. But so all the mathematical background is based on the infinite signal. But in real cases, we're dealing with signal with finite length. So we are actually shifting and shifting to produce an infinite signal. However, for a signal oscillates only non-integer periods in n samples, there will be a jump here. Even if I pad zeros behind that, there will be still a jump. Well, if we just want to pick out the main frequency, actually it does not matter too much, right? But if we want to reconstruct the signal with the frequency spectrum, there will be some problems. Actually, these are all noisy frequencies, but we actually don't have that in our original signal. So windowing is actually a window is for the purpose that to decrease the start and end of the signal to 0. Because if a signal starts from 0 and ends in 0, and if you shift it, there will be no more jump. So all the windows, actually there are many kinds of windows. Many scientists have worked out different windows and different properties, but they all start from 0 and ends with 0. They are triangle windows, and this is a panning window. Let's see what happened after windowing. After windowing, the time series will be like this. And if you shift this signal, there will be no more jump. And let's calculate the spectrum after windowing. You will see that the higher frequency leakage disappears here. But the lower frequency, the frequency next to the main frequency leakage will increase. That seems not good, but actually, in real cases, this will save you a lot, because actually, for example, if you detect some frequency, or in other words, we don't care about the frequency accurate. We care less about the frequency accurate than the high bias. In industry, if you have a frequency very biased to the basic frequency, it will cause, it will bring you a lot of problems. But if you have a frequency here, that's very next to the basic frequency, there won't be too much problems. So that's a trade-off. If you want to decrease the high frequencies, you have to increase the low frequencies. There won't be a win-win solution here. You need to trade off. And different windows have different properties, you might see. And in real case, actually hanging window can solve you maybe 95% of the problems. So that's windowing. Okay, so next is the last thing I want to talk about, the short time Fourier transform. It actually produces a spectrogram for non-stationary audio signal. Well, what's non-stationary audio signal? That means your frequency will change with time. Actually, this is a spectrogram. You must have seen it, right? Let's listen to this. That's a C note and a G note. With the length 1 second and 2 seconds. If we calculate the DFT of this whole length, it will be like this. This is the first 440 frequency, and this is the 660. So it does not make any sense. We want the time resolution. We don't want to know. We want to know when does I mean, I give you a time. You need to give me the frequency, but we don't want a spectrum like this. So that's useless. Then what do I do? First, well, this is the original sine. Well, actually, this is a very dense sine wave. I choose a frame here. Well, it's typically 10 to 25 milliseconds. I draw it very long to make sure you can see it. Okay. So the signal in this frame will be like this. Then I add a window to this signal and do a DFT here. Do a DFT only to this intercepted signal. And actually we get a capital X array here. Well, I write it for short. Okay, we get a capital X array here. And then we move this frame a little bit forward with the hop size. And this hop size can be very small. And we get a second array, right? Okay, let's put all these arrays. No, we repeat this procedure until the frame reaches the end of the signal. And we produce, and we put all the arrays in columns of this matrix, right? The first column stands for the first frame. The second frame. And then we color this matrix. So that's the spectrogram. We color this matrix through sun sheen. You can choose whatever colors you want, but that's the spectrogram. So now I have some questions to ask you. First is, what's the unit of the horizontal and vertical axis of this matrix? Well, for vertical axis, that's the horizontal axis of the spectrogram, right? So that's frequency. But for horizontal axis, you might see it's time, but it's not. It's frames. This frame stands for 0 to 25 milliseconds. So if you tell me I want to know the exact frequency at 20 milliseconds, I'll tell you impossible. If you want to know a frequency, the frequency of a signal, you have to capture a period of it, right? So you can know the frequency and the time simultaneously. So there's a trade-off here. So what will happen if we increase and decrease the frame length? The frame length, I mean this. Well, if we increase the frame length, so for each frame, we contain more periods in the frame. So we get an accuracy frequency calculation. Because if I increase the frame length, this length, I mean the length of this spectrum will also increase. Then we increase the frame resolution, right? So actually, from the spectrogram, you will see that if we increase the frame length, the color will be thinner. Oh, I forgot to give you a. If you look at this, the red line actually is very wide. So we don't know what frequency it is. It might be 300 to 500, right? But if you increase the frame length, the red part will be thinner. But if you decrease the frame length, the red part will be wider. Oh, sorry. I need to go back to that. The red part will be wider. However, if you decrease the frame length, you actually have more accurate time resolution, right? That means this transit will be more clear. We have a transit here, but we don't know what exactly time it is. But if you decrease the frame length, the red line will be wider, and the transit will be thinner. So that's a trade-off. If you choose different frame size, you have different spectrogram. Okay, the last question is, what will happen if we add zeros to the frame before each FFT? Well, that will produce a similar result as for increase the frame length, but a little bit different, because if you increase the frame length, you actually have more information to calculate, then the frequency will be accurate. But if you just add zeros, for some frequency, for some very low frequency, for some very low frequencies, you're not able to detect them by padding zeros, but you can detect them by increase the frame size, right? because the low frequencies have the one period will take very long time, and you might need 3 or 4 periods in the intercepted part to discrete them, to separate them. But if you pack zeros, it will be useless. Okay, so that's probably all I want to talk about today. And if you have questions, maybe you can ask me by email, but not for now. There's another tutorial here.